Okay, I thought I would help you guys on number 26 in section 9.3 because the part E is a little bit tricky and we haven't really gone over something like that in class. So the first few parts are about counting. I think you should be able to get through them pretty quickly. I'll just go ahead and sketch out, what I get for each of these parts. But, pause the video and make sure that you can do all these parts by yourself. Okay, so why don't we pick up with part 16? You're going to want to find a recurrence relation, which means that you want to express Sn in terms of previous SKs. And so if I'm trying to count the number of strings of length n that do not have AA consecutive in them, then I just have to come up with a clever way of counting. And actually, the case n equals 3 is a bit instructive. You can see that if your length 3 string starts with either a B or a C, then basically you have as many length 3 strings as you do length 2 strings for each of B and C. So here I have 8 2-length strings, A, B, A, C, B, A, B, B, and so on. And if I just tack a C onto the left of it, that creates a length 3 string with obviously no consecutive A's in it. And the same with the B. So I'm going to start my count sort of with using that observation. Like the number of strings of length n is going to be 2 Sn minus 1 because you can tack either a B or C onto any n minus 1 length string and create an n length string that way. Now, if I want to count the number of n length strings that start with A, I have to be a little bit more careful, of course, because I don't want to produce a double A in the beginning. So what I can do instead is say, all right, well, if I want a string of length n that starts with A, it better not have A as the next letter. And so I could, either choose a B or a C for the next letter, and then how many counts or how many such strings can I make that way? Well, if I make B the second letter, then I'm going to have strings of length, in this case 1, with no double A's. There's going to be that many that start with AB, and again, how many start with AC? Well, all the length 1 strings. But that generalizes as follows. I can either start with AB or AC and then finish the string with a length n minus 2 string. So this is your recurrence relation, and let's see here. Okay, so part D tells me to just use that to compute S4. You can do that, that's not difficult. Okay, but it's E that I wanted to focus on. So let me show you the procedure for taking this recurrence relation, or one procedure at least, and trying to come up with what's called a closed form solution, or a closed form formula for Sn. So I'm basically looking for a formula for Sn that doesn't make reference to previous counts. Okay, so this is the trick. It's called the characteristic root technique. And what you do is you sort of like guess that Sn is of the form r to the power n, and it might not end up being perfectly r to the power n, as we'll see later, but this algebraic assumption is sort of enough to get the ball rolling, and you'll see how it plays out. So if Sn is r to the n, then I would know, for example, that this equation would look something like this. It would be r to the n equals 2, and then this is the previous term, so that would be r to the n minus 1 plus 2r to the n minus 2. And my goal is to like solve for r. So this is a little equation in r, and I'm just going to try and solve numerically for r. Well, each of these terms has a power of r in it, so I'm going to factor out the biggest that I can, and I'll just go ahead and factor out the negative as well. I'm going to take out r to the n minus 2, and I'm left with r squared in the first term, 2r in the second term. I guess I have a negative there as well. And finally, 2 in the last term. All right, well, this is a quadratic. It's not going to factor, so, well, nicely, so I'm going to go to the quadratic formula. R equals 0 clearly is not going to be an R value that works for Sn because none of the Rn's are, or none of the Sn's are equal to 0. Anyway, so I'm going to put negative b plus or minus square root of b squared minus 4 times a times c. That gives me plus 8 over 2a. And so this is the square root of 12, which is 2 root 3. So I have 1 plus or minus root 3 as my roots. Okay, so now it's not always the case that even though I started with this assumption here that Sn perfectly ends up being one of these roots to the nth power. It turns out it could sort of be any combination of either of these roots to the nth power in the following sense. The best that I actually know is that Sn is going to be some constant multiple of the first root to the nth power plus some constant multiple of the second root to the nth power. So this is what's called a linear combination of powers of each of those roots. And what I'm left to do now is basically solve for the a and the b. So I do know a couple Sn values. They're right over here. I cranked a bunch out. So I'm just going to use the first two values to set up a system of equations in a and b. So I'm going to use the fact that S of 0, well, that would be a plus b, is equal to 1. Did I say 0 up there? Of course I did. Sorry. There's one string of length 0, and that's the empty string. I should have had a 1 there the whole time. Sorry about that. Okay, and then S1, that's going to give me a times 1 plus root 3 plus b 1 minus root 3. That's supposed to equal 3. And what I have now is a system of equations that I can solve for a and b. Plugging those back into my Sn formula here gives me a closed form. So I'll just go through that quickly. You can, well, I'll fast forward when I edit this. Okay, so this finally gives me the closed form expression for Sn, and you can go through and verify the Sn's that we know. If you plug in 0 to this expression, you're going to get 1, and so on. Oops, not doing it right. Okay, I hope that helps.